Hi, this is the first in a series of short videos covering the first part of Chapter 9. So, this is my first time doing this, so bear with me if this is confusing. Okay, so Chapter 9 is about theory again. So, we're going to loop back to the material we started talking about several chapters ago when we talked about atomic theory. So, this time around, we are going to take this to the next level. So, if you recall, the last time we were talking about the other several atomic models, and I told you we were going to finish talking about them a little bit later in the course. So, now is the time for that. Okay, so let's start by reviewing what we had learned in the past about atomic theory. If you recall, we had in the early 1800s, Dalton came up with a theory, basically what I would like to call the kind of the billiard ball model, such that these matter was made up of these individual atoms. Atoms of the same element were identical, but the difference in his case was these were solid indestructible spheres. So now this was a big deal because this is the first time somebody had determined that there were different types of elements and that matter was made up of these different types of elements. So that was quite a momentous occasion when Dalton came up with his theory. As you recall, over the next next 100 years or so, this particular model was expounded to become more and more interesting. So then Thomson did his plum pudding model. In that work, he discovered the negatively charged particle, called that the electron. This was that plum pudding or chocolate chip cookie dough kind of thing we had talked about before. And then eventually Rutherford, in the attempt to build an experiment to prove Thomson's plan, came up with those particles bouncing back, identified there was in fact a nucleus and that the electrons were somehow in the space outside. So just to take us to the next, just to remind us where we were with the last model we had discussed, Rutherford's model of the atom has a dense nucleus where we have protons and neutrons, positively charged and neutral charged particles in the nucleus, surrounded by some negatively charged particles, these electrons, somewhere in an empty space outside. And that the vast majority of the mass of this atom is actually empty space. And then the mass being in the center and the volume, sorry, being empty space in that. So this is where we were. I think this was chapter 3 or 4 that we had talked about this before. So now we're going to jump into where we are moving forward. So Rutherford model had some issues. The If you were to use the rules of classical physics, our standard physics that they had known up until that point, this model of the atom was not going to work. The idea of this orbiting electron as a charged particle, in order for it to continue to orbit, it must be continuing to accelerate. But if it's continuing to accelerate, it will be losing energy. And if that's the case, it should be crashing into the nucleus. And so, and there's a lot of math involved in why classical physics would have predicted that. But basically, the essence was the rules of classical physics, which is what I would call macroscopic physics, the stuff that we're used to. You drop something and it falls, things rolling and following the rules that we're accustomed to seeing with our eyes. Rutherford's model did not follow those rules. He also discovered there was this other thing that happened, we're going to talk about in a little bit. And that is that, we all know if you pass light through a prism or through a raindrop, you get a rainbow. You have the spectrum of white light breaks up into a continuous arc of all of the colors of the rainbow. However, in his case, what was happening is people were finding that if you energized a particular gas and you looked at what was happening, that you were seeing not all the colors, but only specific colors. Okay, so this leads us to the next types of models. We're going to take a hard left really quickly, and we're going to talk about the electromagnetic spectrum. So I want to give you a background on what that is and why how this is related to the emission spectra, so that we can then understand why we had to move forward to a different atomic model. I'm going to pause this video at this point and we'll start a new one in a second.